if you call this reproducing Hilbert space, reproducing kernel Hilbert space, and this one is nice, but you should respect the density as well. So if you want to reduce this cost function, it is okay, but you need to care about the density as well. That's why I put density as well. And the reproducing Hilbert kernel space, HK, is a subset of L2 of R. And we don't know the kernel. We don't know which kernel to use. But we can use the manifold learning idea. And first of all, let's say the distribution is related to density. So this is density and this is distribution. So now the cost function, the regularization term, you just need to minimize gradient of f of x, p of x, the volume of, with respect to manifold M, volume of x. And it turns out that if you just work on that integration by parts, it becomes f of x, Laplacian f of x, p of x, d volume. And if you just discretize that, because now we have some data, it's not continuous, our data is not continuous, so it becomes F transpose L F bar, where F bar is a vector. Is a vector like f of x1, f of xm. So we have m unlabeled data. And you know that I've shown several times that this Laplacian, which is m by m, you can write it as a difference of this diagonal matrix and W. So D is sum over all weights. So this term is just f of xi minus f of xj, wij. And it can be easily proved that when m number of unlabeled data, m goes to infinity, it converges to your actual term, actual continuous regularity objective function. And so finally you can write your objective function yi minus f of xi plus f bar transpose L f bar plus lambda a. This is the ambient regularization term, but here is lambda I, or induced regularization term. This one is for unlabeled data, and this is LA is for ambient, and fk squared. So I want to talk about the article of Mikhail Belkin in a more detailed way. So we have two regularizer. One of them controls complexity of classifier in the ambient space. The other one controls the complexity as measured by, the geometry of the distribution. So geometry of distribution matters. So for this ambient space, I said what? Your regularization is lambda A, and this is lambda induced. So in this article, that manifold regularization, a geometric framework for learning from labeled and unlabeled examples in 2006, they combine three different concepts. First, spectral graph theory, which I talked about it in my previous lectures, spectral graph theory, starting by Chang, 1997. She is a very nice mathematician, and you can watch her YouTube. It's just about mathematics and not about machine learning. The second concept is manifold learning, and the third one is just kernel-based algorithms, such as representation learning and those stuff based off kernel. So we want to combine three different concepts in this article in order to solve semi-supervised learning. First, note that if x1 and x2 in X are close in the intrinsic geometry, it means that P of y conditioned on x1 and P of y conditioned on x2 are similar. So P y conditioned on x, this varies smoothly along the geodesics in the intrinsic geometry of Px. So we can write the cost. So we want to find this labeling function f star, which is the argmin of 1 over L, I from 1 L. This is the labeled data. This is some loss. It could be this loss, which is easy. Plus gamma ambient f squared plus gamma induced f squared. Of course, for SVM, your loss could be maximum of 0 and 1 minus yi f of xi for SVM. But I don't talk about SVM. I just want to talk about semi-supervised learning for regression. And the classical representation theorem that this problem has an easy solution. F star of x is just the sum of alpha I, k, xi, and x. So by this simple trick, I reduce the infinite dimensional problem, which is my favorite, infinite dimensional problem. You reduce it to finite dimensional, because alpha I is finite dimensional. You just need L alpha to make that infinite dimensional function. So first of all, they proved a theorem 1, that assume that induced norm of f is sufficiently smooth with respect to reproducing kernel Hilbert space norm fk, then the solution admits the following representation. So f star of x is now I from 1 to L, alpha I, k, xi, and x, plus alpha z, k, x, and z, dp, x, and z. But we don't know this, okay? And the support, this is the support of p of x. So this is the theorem. And I want to show you for the regularized least square that our problem is just a traditional. First, I start by a very simple problem, which is regularized least square. First, I show you how you can prove it and solve it, find the labeling function. And after that, we go to semi-supervised learning. So if we just substitute f star, which is defined by this representation, alpha I star k x and xi, if you just substitute that, you will notice that you can write this as I from 1 to L yi minus alpha I k x and xi squared plus gamma. You can write it as an inner product of that vector with itself, which you can write k from I from 1 to L, alpha k x and xi. It's so easy, you know. It's you just substitute and solve it. Alpha I star, k x and xi. And you can simply write it as y minus k alpha star transpose y minus k alpha star plus gamma alpha star transpose k alpha star, where k is your gram matrix, which is L by L, because it's fully supervised. So all of them are labeled data. And set is equal to 0. Take derivative, set it equal to 0. So take derivative. Take derivative, it means it is y minus k alpha star transpose. Derivative of that is minus k. This is derivative with respect to alpha. Plus gamma k alpha. This is derivative of this, so this part only. And set it to 0. So alpha star is now easy to obtain. Li minus 1 y. So now I want to work on this again, but this time I add unlabeled data. So we call it Laplacian regularized least square. Laplacian because we are talking about that unsupervised stuff. So it's a lap regularized Laplacian least squares. So the objective function is now the same, except that we add the unlabeled data. Now this is the labeled data, yi minus f of xi plus gamma I, A is ambient, f k squared. Until now, it is fully supervised. Now we consider some unlabeled data as well, which is the induced regularization parameter u plus L squared, F transpose LF, that I proved why it is this. Again, we just write the representation for that to make it finite dimensional and enjoy the finite dimensional space and linear algebra and those things, which is very easy compared to infinite dimensional, which is really hard. So alpha I star is now argmin of 1 over L y minus j k alpha transpose y minus j k alpha plus gamma A alpha transpose k alpha plus gamma induced u plus L squared alpha transpose k L k alpha. Remember that k is now L plus U times L plus U gram matrix. So we have both labeled and unlabeled data in the final term, which is for unlabeled data consideration. And J is all of the diagonal points are the L entries. You have L labeled data, so L entries of that is 1. The rest of that, which is for unlabeled, is 0. Of course, off diagonal is 0 as well. So take derivative with respect to alpha, set it to 0. Let's write it. 1 over L y minus j k alpha minus j k plus gamma k plus gamma I L u plus unlabeled plus labeled squared k L k alpha is equal to 0. So alpha star is now jk plus gamma Li plus gamma I L u plus L squared Lk inverse y. So if gamma I, if this one is 0, then alpha star is just the regularized least square. So if gamma I is 0, then your Laplacian regularized least square, the solution is exactly the regularized least square. Both of them are now equal. So this is the manifold regularization. Of course, there are many other variants of that. For example, deformed graph Laplacian in 2015 by C. Gong in IEEE. Previous methods are not effective for handling ambiguous examples. He has written this quote in his abstract of his paper, and that's why he suggested to use this cost function, which is alpha wij f of xi minus f of xj squared plus 1 over 2 beta I from 1 to n dii j from 1 to n djj f of xi squared plus mu I n L f of xi minus by I squared. Solution is globally optimal. He has proved that it is globally optimal. Also, there is a recent work